Welcome back, my friends. This is William M. Briggs to another episode of Uncertainty and Probability Theory, the Logic of Science. We've finally reached episode 62. The dreaded p-value. The dreaded p-value. P-value, the worst creations in the history of intellectual thought. I think even worse than Marxism in some ways. Although embracing p-values doesn't lead to mass murder. Embracing scientism does, so that's a different thing entirely. And anyway, p-values should die. I'm going to prove that to you at least over one or two videos, possibly even more, because I want you to understand you should never use them. Nobody should ever use them. They should be retired from statistics. They should be retired from probability. They should be retired from science completely. You'll hear a lot of people say after the demonstrations I'm going to give you today, which are mainly going to be logical. I'm going to focus on the logic of p-values today, and they're illogic. Every use of p-value is a fallacy. I'm going to demonstrate that to you, a fallacy. But they're still used, and people often argue, well, all right, Briggs, you might have something there, but p-values still have some good uses. No, they don't. No, they don't. They have no good uses. They should be dumped. They should be thrown out onto the pile and burned with gasoline, and nobody should ever think about them again. Not only should you not use a p-value, you should never trust any research that uses p-values or confidence intervals. We'll come to confidence intervals in a little while. There's three basic focuses on p-values that I want to emphasize, because we're trying to think about evidence, right? We're trying to ask, what's the probability our hypothesis is true, whatever that hypothesis is going to be, whether it's causal, it's just some proposition, anything, any kind of proposition we want to put in there, we know that. Given whatever evidence that we assume, our evidence, and we want to know this, we want to know the probability that hypothesis is true, given whatever evidence that we have. That's what we have done from day one. We know that this is a very good thing to do. So let's now define the p-value. Oh, before I do that, I want to talk about the three basic areas of p-values that were in the thinking about evidence as it's traditionally used in probability and statistics and physics everywhere. That is, the first is logical. We're going to do mostly logical today. The logic of the matter, what does it mean about evidence, all that kind of thing. The next is, I don't know what order I'm going to do all these in, but the three of them are parameters. The parameter-based obsession that people have with models and the deadly sin of reification and so forth. And the third, these are all together the same thing really, but I don't think I could fit them all into one lecture. I've already burned 3 minutes here. And the third is causality. We're interested in causality in science and in daily life as well. And so we want to know, what can p-values tell us about causality? The answer is nothing. But people do tend to think p-values tell them about causality. They're making a mistake. This tells us about causality, or gives us hints about causality. We'll talk about causality in depth too in separate lectures, because we're going to build these models. We're going to say, what can these models tell us about cause? And because that's what we want to know. And science has been very successful in that field, building toys where causes are posited, causes are proved, and then they're made into things, made into objects and so forth. But this is not the majority of science. The majority of science is stuff you never see. It turns out to be wrong or exaggerated or unimportant and things like this. And a lot of it has to do with this p-value stuff. So today, logic, and the next time either I'll do them together, depending on how short I can make it, parameters and parameter obsession and cause. So we'll see how we do it all. So let's define the p-value. The p-value is the probability of data we didn't see given the hypothesis, whatever hypothesis we're entertaining, is false. This equals p, or little p, or capital P, however you want to do it. This is the p-value. Right there. Well, we want this. I hope you agree we want this. We get this. Is this object here, this thing? It's not a trick question. Is this object in any way resemble that thing? What we know we could do this. We saw the last couple of weeks I did examples of where we did just this. And we're going to continue on doing many more examples where we could do just this. We could just do this. But is that anything like this? Do they even look alike to you? So now let's talk about this. We have to remember two things. Well, one of them you haven't heard before, but in frequentist theory, it is a fact, a dictum, a dogma of frequentist theory. Some dogma's good, some dogma's bad. Remember that. We talked about that too before. Dogma itself is not a problem. The word's not a problem. And the things that we're asked to believe under dogma, are they true or not? That's the only thing we care about. Are they universally true? Are they universally true? Are they necessarily true? Those bits of dogma we're asked to believe, we should. We're making mistakes when we don't believe the truth with a capital T truth. And you'll hear some people, we already did this a long time ago. Some people will insist, we know for a fact there are no truths. Humans can't know truths. They'll say things like this. Our senses are fallible and therefore we cannot know any truth. Aha! What do you say to people like that? Do you say, is it true we can't know any truth? Yes, it's absolutely true we can't know any truth. Well, the best thing we could do with that kind of stuff is just ignore it. It's silly, but it's pervasive. Anyway, in frequentist theory, it's dogma. No proposition, no non-physical object. So no propositions. Propositions are not physical objects. No proposition can have a probability in our sense, can have a probability like this, can be calculated. No probability, no proposition can have a probability calculated for it, or assigned, or assumed, or anything. This just cannot be. That's the theory. That's in part of the theory. The theory has, the frequentist theory is that objects are embedded in infinite sequences of certain measures, or rather functions, are embedded in infinite sequences, and they have to have an infinite number, or at least possibility, in order for frequentist theory to apply, and therefore this is true. Everybody violates, as I've told you many times. There's a lot of people who calculate frequentist theories and they talk about in the long runs and all this kind of stuff, but there's absolutely not one consistent frequentist on the planet, just like there's no solipsists or anything like this. There's people who might claim it, but they're never consistent with this. So now let's do this. There's a fact that we deduce in this, which I'm not going to bother to deduce, but it's a fact. It's a frequentist theory fact. It's a theorem, I should say, but the fact is good enough from frequentist theory that the p-value, see, they'll say something like this, is uniformly distributed. Now, we know that this kind of language is forbidden to us because probability does not exist. Probability doesn't inhere in things like frequentists believe. So they'll say probability is uniformly distributed, which is to say this. Under the null, if, we're going to have a logical argument here, if HF is true, now I'm going to use HF to say it, whatever hypothesis we want, we take the logical contrary of that, and that, we remember, is, in frequentist lingo, the null. If the null is true, the p-value is uniform on 0, 1. This is a deduction, assuming frequentist theory is true, which we'll accept for the sake of argument as we're going here. So if the null is true, the p-value has any particular value. Now, why do we speak like this? I'm going to read you this quote. I once wrote this in an article for David Berlinski, and I said the following, and he rightly castigated me for getting it wrong, for getting my logic wrong, which just goes to show you how difficult this is. Well, no, it doesn't go to show you. I make many mistakes, but maybe you're somebody else who doesn't. This is what Fisher has said before, R.A. Fisher. He's the guy who invented these p-values. He said, belief in the null hypothesis as an accurate representation of the population sampled is confronted by a logical disjunction. Either the null is false, either the null is false, so H is HF false, or P is we by chance. And Fisher called this a logical disjunction. In an article I wrote for Interference, David Berlinski's Interference, which he rightly rejected, I said this is not a logical disjunction. I should have said this is a logical disjunction. Of course it is. But it is a rotten logical disjunction. It is a terrible logical disjunction, which is what we're going to see right here. First of all, we already know nothing is by chance. Nothing is by chance. Chance can't cause anything, but maybe he didn't mean that. Maybe he meant something else. So we need to tighten. Maybe that's not the problem with this. Or HF is false, the null is false. But I want to ask you here. Since the null is the logical opposite of the hypothesis in which we're interested in, if we're saying HF is false, what are we saying? This is not a trick question. Yes, okay, H true. That is a fact. If this is false, if the null hypothesis is false, which is to say, if the hypothesis in which we're interested in is true, either that's true or we got a wee p-value by chance. We're already starting to see some difficulties here, but maybe you don't see it. So I'm gonna use this little logical argument in the old-fashioned kind of a way of writing these things. If the null is true, the p-value is uniformly distributed. In other words, this is in frequentist lingo, which we don't buy, but they say the p-value is equally likely to be any value in 0, 1. That's all that means. It means it can be any value. It could be, it can't be 1 or 0. The ends here are not. These are not brackets. It's the open interval between 0 and 1. It can be any value in there, and each of these is equally likely. That's the thing right here. Now, here's the logical argument. Let's suppose the null, N-U-L-L, is true. Okay. Here's our first premise. Here's our second premise. And we got this right here. Now we actually, and we're going to calculate our data, we get a wee p, which is a p-value less than the magic number, which I revealed to us last week is 0.05. Okay? We see this. These are our premises. This is a theoretical statement. Here we're going to assume the null is true, and we got a wee p. So now what do? We reject the null. This is the term they use. They reject the null. Now you're rejecting the null. You're saying that HF is false. Here's another word for saying this. Yes, rejecting the null. You're rejecting the null. In other words, you're not accepting that the null is HF is true. You're saying HF is false, which is another way of saying H is true. So, all of these are equivalent. The rejecting the null, HF is false, is just same exact thing written in notation. And HF is false is to say, because HF is the logical contrary of H is true. The hypothesis is true. So, if HF is true, the null is true. Another way to say that is if H is false. If the hypothesis is false, the p-value could be anything we like. The hypothesis is false. Okay, we're saying the hypothesis is false here, and we get a wee p-value. We see a wee p-value, and we're going to calculate these when we do a lot of calculations and so forth. Then we're going to say H is true. One of our premises was H is false, and now we're going to accept that H is true. This is a fallacy. This is a logical fallacy. It is and this part I got right in the article, and I've written about this several times in many different ways. There's all kind of things wrong with p-values. This is the main problem right here. It is a fallacious use. It's a fallacy. You cannot start with that H is false and say if the hypothesis is false, the p-value could be anything, and then you assume the hypothesis is false, and then you get this wee p-value here. We get any value. We get any value. This says any value is equally likely, and then we get a value, which is any value. This right here is any value. This, importantly, this wouldn't be a this would not be a fallacy. We could say that H is false, and let me. God, I tend to get so animated about this. I hope you see what I'm trying to say here. Let me step through it again. Because I can't get people to understand this. It's probably my fault. Probably the way I'm putting this stuff is my fault. Let's change our first premise right here. We're going to say if H is false, H false. That's another way of saying this. We get P less than magic number. Okay? Now we're going to assume H is false. And then we get a we P. Now, what can we conclude? If H is false, we get a we P. H we're going to assume is false. We get a we P. And what can we assume? That H, of course, what can we assume with this? Now, you can't get there from here is the very point of this. If HF is true, if H is false, we get the we P value. We're going to then assume that H is false. We get a we P value. Then we can say H is false. Well, that's okay. We can say that. That's not what people do, but this is valid. This is a valid thing. Okay, we could do this. We could say if H is false, if H is true, let's say this. Let's see. Let's just make we're trying to make logical, valid arguments of this. We can say if H is true, we get a we P value. We get a we P value. Therefore, we could say H is true. That's a valid argument. Yes? If H is true, we get a we P value. We see a we P value. If A, then B. Well, we need to still assume that H is true. And we get a we P value, and we can conclude H is true. If we had concluded H is false from this, we'd be making if we instead concluded that H is false from this, we'd be making a fallacy. There's no way to rescue this. There's no way to rescue this. This here says we get a we P. This first premise says nothing about the value of the P except that every value is equally likely. And we're not allowed, you got to remember, in frequentist theory, we're not allowed to say anything about the probability of this thing right here. But we've rejected the null. We reject the null, and then we're claiming H is true, which is another way of saying the probability of H, given the evidence, is 1. If you're saying something is true, it could be a local truth. That's perfectly fine. We can get a local truth out of this kind of thing and not a necessary truth. It doesn't mean that we have proved a universal necessary truth. Remember, we got lots of local truths that we showed how that thing goes. This kind of thing is possible, absolutely possible, but it's forbidden. I erased it to make probability statements about these hypotheses. This is an act. It is an act. It does not say that the probability of this equals high. It does not say it is 0.95. It does not say that the probability that HF, therefore, is true equals 0.05. It's none of these things. It's this. They say when you're rejecting this, but they don't say that. They'll say they'll say this. This little sidetrack right here is just to show you we can rescue the thing as long as we change this first premise up here, which of course we don't do. People will say when you get smaller, the weirder the P, the stronger the belief, or the stronger the belief or evidence in favor of H, which is to say the probability of H given whatever evidence and the P size is this. The probability of H depends on the p size, and the smaller this gets, the bigger this gets. That's forbidden in frequentist theory. You can't get there from here. There's absolutely no way to jump from a wee p-value to any kind of statement about the hypothesis at hand. None. It doesn't exist. You can't get it from this. You can't get it from the premise. You can't get it from the premise. The whole premise of frequentism is that if the null is true, you get any p-value. You assume the null is true, and you get a wee p-value. And then you conclude the null is false, which is to say the hypothesis itself is true. You can't get there. It is a logical fallacy. It is a fallacy. It is a fallacious move. And then the fallacy number 2 comes in correlating, if you like, in the plain English sense of that word, the size of the p, the smaller the p is, with the larger this probability is, which is forbidden. You're not allowed to assign this any probability. It's either true or false. That's it. Like I say, there's absolutely no consistent frequentists out there. They do not exist. Now, this is only the first thing. We've already gone 21 minutes into this thing. I've only shown you the first thing wrong with p-values. There's absolutely no reason to do this, not when we can calculate directly the hypothesis of interest is true, given what the evidence. We did learn it can be brutally complicated to do this, right? This evidence here you change. This is one thing that frequentists don't like. They'll say when you change this evidence, you change the probability the hypothesis is true, because in their mind the hypothesis is only true or false. Well, yeah, that's true. The hypothesis is only true or false, but that's the ontology of it, if you like. The epistemology of it is your knowledge of the hypothesis. This is the fundamental error that is made over and over again. It's made in physics, it's made in chemistry, it's made in every so-called soft sciences on an absolutely, I want to say hourly, but I think even minutely basis. This is an epistemological statement. It has nothing to do with whether and these things can be just regular propositions, right? They don't have to, it's not saying anything about reality per se unless it's in your evidence and in the hypothesis itself. Yes, you change the evidence, you change the probability. That is not a bug, it is a feature. And we've done this so many times. I mean, just endless times. Your knowledge may be different than my knowledge, therefore the probabilities we have about the truth of this can be completely different. Here, even if this was a non-fallacious argument, it is still a decision. It is a decision. It is to say, okay, maybe I can't, because I'm not allowed to assign a probability to this H is true business, but I'm going to act like it's true. I'm going to act like this. Now that, my dear, is a decision. That is a decision you're making for everybody. If the probability of this is, let's just say the probability of some hypothesis that the new drug is going to work. The new drug is going to work. And remember, we have to define what we mean by work and all this kind of stuff. But here we're going to skate over. We did that for, 3 or 4 weeks in a row. But we got all that in mind. We got the new drug. Suppose it's 60% or 70%. Let's bump it up and be generous. The probability is 0.7. That's what we calculate doing it the correct way. Here in this way, they say it's true. It's absolutely going to work. They're going to act like it's going to work. You have to act like it's going to work. That is a decision that you have made. What's the consequences of those decisions? Those consequences depend entirely on the uses to which those decisions will be put. They can vary from anybody, right? A fancy way to say it, if you know these terms, which we'll get to, is the loss functions of everybody can be different. The loss function of your doctor is entirely different from your loss function. He's got entirely different goals that you hope that he has some of the same shared goals, but they're not all the same as you're not the one, he's not the one who's going to suffer any side effects, for instance, which this doesn't even answer. Now, nobody is a consistent frequentist. Nobody who uses p-values is consistent in the way p-values should be used. But you'll see other things like this. Well, all right, Briggs, I kind of get what you mean here. You're kind of raving and incoherent, and I'm not quite following you. Maybe I'll come back and read this stuff again sometime and look at it. I'll have links for you at the regular places, wmbriggs.com, wmbriggs.substack.com. But you know, I've seen many of the times, here's another argument. Many of the times I've seen a wee p, the hypothesis turned out to be true. Many of the times I've seen a wee p, the hypothesis turned out to be true. Therefore, in this case, the hypothesis is true because wee p. Well, again, this is putting a probability on a hypothesis, which is forbidden by frequentist theory. You can't do that. And this actually can have an interpretation in logic. And here's where it seems to fool people, because this can have an interpretation in logic. You can't do it in frequentism. You can't use it in p-values. I got all the windows open and wasps are flying in. You can have an interpretation. Look, at least in olden days, and in many cases still, a lot of scientists pick good hypotheses. They pick good hypotheses that are probably true they're probably true, or the strength of an association they're claiming is probably there, but maybe not as strong as they're claiming. That's a kind of hypothesis will meet all these kind of things. So they pick good hypotheses. All right, they pick good hypotheses. Not all of them. There's just lots and lots of lousy ones. You see, I've covered them for years, especially in climate science and COVID and all these kinds of things. They pick absolutely lousy hypotheses, and they confirm them with these wee p-value nonsense things, which we'll see in another lecture. And so this is the idea that, well, yeah, they're kind of picking good hypotheses, and maybe the p is we in those kind of cases, and that's what they're thinking. Therefore, this one's probably likely right too. And that's a reasonable argument, but it's based on an implicit premise that this p-value is giving you any kind of information. And the second implicit premises, I should have said, the second premise is that you know, they've done this thing well. The particular one you're looking at is done well. I forgot another thing of logic I wanted to do here. Oh, rats. I wrote it down. This is absolutely true. Well, yes, here we go. Let's just do all this right here. Let's come back over to this right here. This is kind of funny. Okay. Let's do this. Okay, if the hypothesis is false, in other words, if the null is true, we get any kind of p-value. We're going to assume that the null is true. Now we get a p greater than the magic number, and now they fail to reject reject the null. This kind of bizarre language, is that the same as accept the null? In other words, is it a high probability that HF is high? This is a bizarre formulation no matter how you do it. You fail to reject the null. This is that Popperian falsifiability stuff we've talked about before. You need to be able to falsify things. Well, that's neither here nor there. We talked about that before. I don't want to get into it now. But you fail to reject the null, meaning you can reject, meaning you'll reject it later? It's not true? What if it is true? I mean, we could have all kinds of things where there's absolutely no causal connection, and that could be our null, and we know that they're false based on other information. We know that this equals 0 based on other information that we have, and therefore the null, the HF, is absolutely true. But you're not allowed to do that. And it's not used, this is what I'm saying here. This is the next thing the logic is. And I don't have time to do this. I'll tie it in with cause. The p-values are not used consistently. They're not used all the time. Frequentist theory demands that this is how you evaluate every hypothesis. But of course people don't. They accept all kind of them like this, in this fashion openly. So the p-values are only used, it seems, when information is dicey, when there's no real clear connection and all kind of other things that can be going on. And so that's a big reason to distrust p-values. But in any case, we have demonstrated every single use is a logical fallacy. There's no question about that. All right, that's it for this time. See wmbriggs.com and wmbriggssubstack.com, and that's it for this time. Thanks for watching.